Okay. So this is the simulation that we are going to use to understand the projectile motion. Let me tell you what are the parameters available in this simulation. First of all, you see a body that is going to be projected. Then this is the initial velocity that you can control and give it to the body. This is the angle with which you can choose to fire the body. These are the various velocities, that is the total velocity, x component of velocity, y component of velocity, and finally the acceleration due to gravity. Using these buttons, you can either see them or you can hide them. And this is the initial velocity of the body, the angle with which it is projected, x component of velocity at any point of its motion, y component of its velocity at any points of its motion, present x coordinate, present y coordinate, the instant of time, the angle made by the velocity vector with respect to the horizontal, and finally, how far will the body go and how high will the body go. These are the various parameters. So as you see, presently, the initial velocity is set at 80. The angle of projection is set at 60. Without viewing any of the vectors, let us just see how does the body move. There you go. This is how the body moves. It reaches the highest point, follows a nice curved path, and then it reaches the ground. This is, always, known to us through our day-to-day life observations. So we will reload it. And this time we will look at x component of velocity. When I say x component of velocity, observe this blue vector here. And as the body moves, see whether this blue vector changes in magnitude or direction or both. Here we go. I think by now you might have observed it that the blue vector, which is used to represent the x component of velocity, did not change in magnitude. It did not change in direction. What does the vertical component of velocity do? Now let us see this. You see the vertical blue component? Here it is. It is decreasing, becomes 0, and then starts increasing in the downward direction. Very clearly it is observed. Now the question is, who's responsible for all this? As I told you earlier, it is acceleration due to gravity that is responsible for all this. So let us see acceleration due to gravity. See, this is the acceleration due to gravity. I'll just pause it here and move it step by step. You see, as we move it step by step, you can see that the vertical component of velocity is decreasing. There is no change in the acceleration due to gravity. Observe that. The vertical component of velocity is decreasing. It has become 0 at the highest point, but it doesn't remain 0 there because acceleration due to gravity will still be acting on it. And slowly the vertical component of velocity increases in the downward direction. You can see that vector coming out now. Right? This process continues and therefore the body falls down. While all this happens, what happens to the total velocity of the body? Let us remove these two and look at the total velocity or the instantaneous velocity of the body. There you see. Few interesting things to observe here. For instantaneous velocity, neither is the magnitude constant nor is the direction constant. And one more important thing, which I'll just let you know just by drawing instantaneous velocities at various points. Let us play it, pause, and let us draw the instantaneous velocity vector. I mean, there is a vector that is already drawn in the simulation. Let us top it up with another one here. There I have drawn it. Now let us let it go. And at this point, let us pause it and draw another instantaneous velocity vector, just drawing on the top of the given vector. Then let it go again. And here again, let us draw it. So we draw a vector on top of it, just for a reference. And later on, I'll tell you why I'm doing all this. And let us pause it here and draw another vector here, right on top of it. And let it go again. Right. So here you see at any of these points, either at point A or point B or point C or point D, at any of these points, the instantaneous velocity vector that was V, this one was always tangential. Right? Tangential to what? Tangential to the path followed by the body. There are so many things that we can understand. Furthermore, let us look at one more thing. For angle 60, with the initial velocity of projection as 80, we saw that the range was 554.26. Let us reload it and let us decrease the angle. Remember, it was 554.26. Let us decrease the angle to 30. 500. Remember the range. See, 554.26. How is it possible that I have changed the angle terribly from 60, I have brought it to 30, still the range is same? These are the things that we will analyze using our derivations. Okay, so that's all for this small sample recording. Probably once in the class, we will look at the derivations and then we will compare those output from the derivations with the simulations. Again, we'll go back to derivations. Again, we'll come back to simulations. We'll keep using it like this, right? Thank you very much, everyone.